Colors are important for life. They are used in nature for communication. Birds advertise to find the best mate, and flowers try to stand out to attract more pollinators. But what about us humans? How do colors affect us? Let's look at an example. Which cereal box would you choose? The colorful one is more attractive, but it also has some information. Yellow and orange that remind us of grains, and green that makes us feel like this is probably healthy. In hospital corridor, blue colors may help us feel calmer. Some companies even trademark colors, like Mazda red and the purple color of Milka chocolate. These companies trademark colors because they understand how important color is. It affects what we will buy and how we feel. In fact, almost every industry heavily uses color. Food, textile, and even medicine. But have you ever thought how all this color is created? Most industries rely on pigments. But what is a pigment? A pigment is a molecule. This plant is green because it is full of green pigment molecules. Sunlight emits all wavelengths of color, but the pigment molecule is absorbing all colors or swallowing them, except the green color, which is why we see green. Pigments can also be man-made or synthetically made. In fact, most industries rely on synthetic pigments that are harmful for the environment and our health. And these pigments also fade over time. But there's a different way of making color that doesn't use any pigments at all. This is called structural color. This is the morpho butterfly. Its blue wings don't contain any pigment at all. They are made of a completely transparent material. The color is formed by a structure hidden from the naked eye. Every time light hits a boundary between two materials, some of the light is reflected back, and some is transmitted through the material. The color of the reflected light depends on the distance between the layers. So if I change the distance between the layers, we will observe a different color. And if I ruin the structure altogether or grind it into a powder, it will be colorless. Nature is the master of structural coloration. Plants, animals, and even single cellular organisms create different colors from in many different configurations from many different materials. The most recognizable form of structural color are iridescent color that can change with the angle of viewing. And this isn't achievable with regular pigments. There are even mammals that use collagen, exactly the same material we have in our skin, to create bright blue coloration. The only difference is the way the material is organized. In my research, we aim to characterize the chemistry and the physics behind these colors, and then try to understand how these animals are making them. And we do this because we want to eventually try to imitate them in the lab. But why would we want to imitate them if there's already so much color around us? So this is a 150-year-old plant. It's been dead for years. Its leaves used to be green from pigment, but the pigment has completely faded. But the blue color of the fruit is a structural color that remained exactly as it was years ago. Structural colors don't fade and can be made from natural materials, which makes them much more sustainable than pigments. But the real reason we're interested in structural colors is that they can be ultra efficient. And this brings me to my own research. I want to introduce you guys to one of our most intriguing subjects, the cleaner shrimp. This shrimp has a very bright white stripe on its back. This color remains bright even deep in the ocean where there's not much light. It evolved over hundreds of millions of years of evolution with the goal to become the brightest white using the least amount of resources. Its life literally depends on it. So let's see what the shrimp came up with. This color is ultra thin. It is 10 times thinner than the diameter of a human hair. If we wanted to make the same color with a conventional white paint, we would need 50 times more material. Imagine we can save tons of time and money over all these industries and replace harmful pigments. So in order to imitate it, we need to understand it. And we do this by first looking at the structure of the color and the chemistry, or what it's made of. If we want to look at structures smaller than visible light, we can't use just a normal microscope. We need an electron microscope. Inside of the electron microscope, there's a very high vacuum. So what do you think will happen if I put this grape inside a very high vacuum? It will turn into this. And since structure is really important for us, we want to look at the material in its native state, like the grape. So we need to freeze it. But if I just freeze it normally, it would be full of ice, which also obstructs the structure. So to overcome this, we vitrify the material, which practically means freezing it really fast to really low temperatures. In less than half a second, we freeze the samples 190 degrees Celsius. So after we froze the sample, we can look at the material with an electron microscope. And what we see is the structure creating the white coloration. And it's just a bunch of really tiny spheres. Each of these is 50 times smaller than the diameter of a human hair. But after we've done all this sample preparation, if we compare it to the structure of a conventional white paint, they're actually quite similar. So why would we need 50 times more material of a conventional white paint to achieve the same color? The shrimp has a secret. If we slice one of these tiny spheres, we reveal a spoke-like structure, kind of like a sea urchin. The spokes tell us about the arrangement of molecules inside of the sphere. So let's imagine each one of these spheres is like a disco ball. Each one of these little mirrors is like a molecule. The mirror has a reflective side and a non-reflective side. If we flip the mirrors to their non-reflective side, we will just get a regular non-reflective ball. We can also just take all the mirrors and bunch them together into a ball, randomly oriented mirrors. But the specific orientation of molecules in the sphere, like the arrangement of mirrors in a disco ball, gives the sphere a special optical property called birefringence. Birefringence means that when light hits the sphere, it splits. So it increases light scattering. So if we go back to the structures, every tiny sphere in the cleaner shrimp is like a disco ball, enhancing the scattering of light. But in the conventional white paint, the particles are not birefringent, which means we need much more material to achieve the same light scattering. In this research, we set out to understand a natural phenomenon. But through the process, we also discovered a new fundamental concept in optics, that birefringence enhances scattering. And this shows us that we can be inspired by nature, but we can also learn new fundamental things. And now, all that is left to do is create new and better materials using what we've learned from those who have been here before us and will probably be here after us.
Any questions?
Hi, thank you for the talk, all from the Weizmann Institute. So I guess in order to create such complicated structures, there needs to be kind of a strong evolutionary pressure to create this kind of thing. So specifically for the shrimp, which kind of evolutionary pressure can you imagine that creates such a thing?
Yeah, so I would just say this is not part of my research. This is more like a biological behavior research, but I do know the answer. So these cleaner shrimp in nature, they kind of like have a symbiotic relationship with larger fish, and they kind of like hop on larger fish and eat parasites off them. That's why they're called cleaner shrimp. And it's been shown in different research, not mine, that these fish recognize the cleaner shrimp from the very bright stripe they have on their back. And different species of cleaner shrimp also have like big stripe-like features that help the fish recognize that these are cleaner shrimp, because alternatively they can also be their natural prey.
Hello, Dana from Hebrew University. Thank you, so beautiful. If you want to use the structural color in industry, is it a problem if material dents, for example? Because you said if you pulverize it, it loses the color. So how do you compensate for those disadvantages?
So yes, there are different types of structural colors used in industry, although most are pigments. And yes, if your structural color will be efficient only in a specific configuration. So if you make it too dense, then it might change. And some strategies they use in the industry to overcome this are like spacers. So you can put kind of like other material in between your structure to hold space, kind of. Yeah.
Thank you very much. Sorry, another question.
Hey, thank you for the talk. Tomer from the Hebrew University. I wondered if like structure coloration can be applied in the clothing industry, or is it a problem? Because I know this is one of the most the industries that uses it harms the environment and everything. But I guess how can it be applied on clothes, or it's
Yeah. To be honest, I'm not 100% sure, because I'm not like we're more into like the basic science side and not very much in the application. But I do know that there are some structural color textiles. It's not, I don't think, very commonly used. Yeah.
Thank you.
Thank you very much.